Cool and cool. All right. So today is the 23rd of April here at ASU. We are moving on from Windows and going back to the glorious land of Linux. If you like the Windows stuff, there are plans for more Windows content, but it's not happening in the next couple weeks. We have to wrap up this class. And so we are moving on to kernel exploitation. Memes. So this module is new, and all new modules, especially if I create them, are potential dumpster fires, but I don't think this one is that bad. One of the ideas here with a lot of our challenges, in particular this Windows one, was to kind of progressively move where Rob Defender or the kind of CDR is putting its claws in to make it more difficult for you to figure out what to do. Right? And so if you follow the natural progression, then this is kind of your experience. Now, somebody here said there's a way around that, right? If I know this is a logical progression where what I think, hopefully what the user thinks is what gets blocked in the next challenge, I could just look ahead and then do whatever is now blocked. And all right, you could do that. I think that ruins a little bit of the educational value, but I'm not going to be mad if you try and game the system, right? There are things that I thought about doing without even going. So I mentioned, I guess in class, I think last week, that I could have, if I had the time, which I didn't, I could have hooked in the actual kernel itself and stopped you from literally doing systems. And somebody asked me on the Discord, well, how would you do that? And I talked about it a little bit. Even without doing that, there is an extension of this natural progression that is more pain than this, that I thought of, to where unless you are very, very clever, now I did discuss how you would solve this challenge that doesn't exist already, or hinted at it, you would not be able to do any of the stuff at all. Like, wouldn't be able to file, wouldn't be able to start process, wouldn't be able to do anything. Everything is hooked at NTDLL. And I think that would be fun. I could stop you from calling syscalls in the executable, and you could still get around it. Right? There's several more continuation challenges that I could add without having to go into the kernel. That would be even more messed up there, which I think would be fun, but I think you guys would disagree based on the initial feedback I've got. This is kind of the key to success here in the middle for the Windows stuff. I'm not trying to purposely obscure what Rob Defender was doing. There is a clearly named file, rd rules, inside challenge rd, that kind of informs you as far as what is Rob Defender doing and where is it placing its hooks. In a more realistic scenario, you wouldn't necessarily know that, and you would have to figure that out. But I think that's the wrong kind of pain for this class. I'd rather have you spend time trying to get around the problem instead of figuring out what the problem is. Course logistics. So somehow, between spring break and now, a lot of time went by. I'm not sure what we did, but it happened, right? We have I think 2 weeks left in the class. Next semester, or not next semester, next week we get last week class. Finals week falls after that. I don't have this room for finals week, so that means next week is the final, or is the last week of class. We'll still talk about kernel stuff. I do intend on holding office hours over finals week, so that means if you are stuck on something in Windows or you are stuck on something with kernel, we can, outside of class, synchronize and try and get you on stuff. Hopefully everything is posted to the grades page. If it is not, let me know. If anything looks wrong, let me know. This includes extra credit, etc. If anything is amiss, let me know now. At the end of the semester, things get weird. Any questions about the course itself? Beautiful. All right, we get to our last and final slide. Demos. So I'm going to do a quick run through of kind of kernel heap thinking about it. I'm going to reuse some of the pre-recorded slides. I don't plan on spending forever repeating what is pre-recorded. but I want to touch on it so that way we're all on the same page, talking to people. It's kind of hitting this as far as what people have seen from the existing content. As I run through the slides, I'm going to then talk about how we can like look at and think about the kernel heap, but we can't discuss what we're looking at until we understand how it worked to begin with. And we'll look at a few different ways to do that. The thing that I hope people focus on is this libslub, which I did not cover that much in the pre-recorded lectures. The question from Twitch is this the easy kernel or the hard kernel? This is the hard kernel. Traditionally, this module run is competing for hardest module on the site that is not in the quarterly list. The general concept is still heap corruption. So these kind of things that we learned from dynamic allocator exploitation, these concepts still apply. It's just, again, a different shape of the heap and how the heap behaves and what metadata is available to you to mess around with. And then lastly, if we have time, we're going to talk about mod probe path, which is kind of an infamous technique to get execution from the kernel. I don't know if we'll have time to touch on that. Okay, so kernel heap. The kernel heap uses something that is called a slab allocator. And the reason for that is the Linux kernel has a very different use case, right? What happens in libc or in user land if you malloc a bunch of stuff and you free a bunch of stuff and you malloc a bunch of stuff and free a bunch of stuff and that the heap gets all like fragmented and messed up? Is that the end of the world? No, not really, right? Like it's not good, but it's not the end of the world. The Linux kernel, though, how long is the Linux kernel supposed to run? As long as the system is running. If the kernel stops running, your entire system grinds to a halt, right? And so if we need to have a dynamic allocation, which we do in the kernel to just function, we need to have a different strategy for how we deal with these dynamic allocations because we cannot make a mistake. If the kernel makes a mistake, everything breaks. So the kernel needs to be insanely performant, and it needs to be insanely efficient when it comes to space and in terms of time. And the way that the kernel does this is via something that's called a slab allocator. Now, I'm using the term slab in the general sense that this is a class or type of heap allocation strategy, not that it is specifically the slab allocator within the Linux implementation context. This idea of the slab allocator actually exists in other operating systems as well. For instance, Mac OS uses a slab style allocator, which has a lot of the same properties as what we're going to discuss today. So slab allocators have been around for a long time. There are 3 implementations that are used on Linux, although in practice there's really only one. And so we are going to be talking about the slub implementation of the slab allocator style. There is, in fact, a slab implementation of the slab allocator, but this is deprecated. And then there's also the slob implementation. You will almost never see slab. You will occasionally see slob on like embedded devices, but that's kind of out of scope for what we're doing in this class. On a modern Linux system, slub is the default implementation of a slab allocator, and that is what we're going to talk about today. So everything we talk about today is the slub implementation of a slab allocator. Terminology. Okay, so slab allocators look completely different than kind of what we know from libc. We start with this concept of a slab, right? That's why we call them slab allocators. A slab is typically a page of memory at the minimum. It could be larger than a page, it could be multiple pages, but typically it's a page of memory. Okay? This slab is broken up into slots for a specific size of object, right? So we don't start from, hey, I need to malloc something. Instead, we start from, well, what kind of objects do we dynamically allocate, right? Maybe we need to allocate a bunch of 512 byte things. What we would do is we would make a cache that exists for 525 or 512 byte objects. That slab would consist of a page that is broken up into a number of slots that are all 512 bytes in size. Does that kind of make sense? All right.
So yes, is the cache 512 bytes in size?
No, the cache is the highest level abstraction of this model. All right. The cache is the, I'm going to call it the management data structure. It holds metadata that is specific to the type of allocations that are going to occur within it. So we can think of a cache as a bucket that exists to manage a specific size of allocation. So there is a cache for instance, 512 bytes. And this is like a real thing. We can see this. Let's VM start. It's VM connect. You will notice on this module in particular, it is the world's slowest VM. I keep lying to myself and saying that we're going to fix that, but there's reasons, and the reasons are not only technical on our side from the infrastructure, but also to your benefit, which I'll touch on a little bit later in the slide. Because this VM is single-threaded. That's okay. That's okay. I'm still a believer. It's just so slow, you see, that you have to just give it a minute to connect again. There we go. Yeah. You know, that one thread is firing real quick. Twitch makes the observation that pwn.college is down, I think. So there is, as of right now, some issue with the web server displaying but SSH works. And so instead of delaying class and this time for me to debug that, there are other people who are looking into that. And since SSH works, that's all I need to be a talking head. So hopefully the bigger brains are on it. Okay, so I'm inside this VM, and the first thing that I said I'm going to demo is how do we look at these allocations via proc. All right, I've noticed that I'm in practice mode, and so we've already seen inside proc. I should be more good with the commands I run in hindsight, but we've already seen that we can list the functions that exist inside the kernel, right? With what is it? KL6. Right? There is another thing that we can access via proc that's a pseudo file system. I believe it's slab info. Let's see if I'm right here. We can't proc. I need a sudo. And this is a pseudo file, very similar to everything in proc, that is going to give us metadata about all of these caches that exist inside the kernel, assuming the VM abides. And what we'll see, hopefully, is that there's going to be, I'm going to say 40 to 60 different lines of text here. We're going to see a row of names along the left-hand side. These are going to have names such as kmalloc 512, kmalloc 256, kmalloc CG 512, right? We'll touch on the CG here in a little bit. I said, what if there's 512 or 256? This is literally the cache that I just described, right? This is a cache that exists inside the kernel to deal with 520 or 512 byte objects.
So does the cache only have metadata about the slabs? Is that right? Is that a correct way of thinking?
Can you rephrase the question?
From my understanding is these different size caches are just like cache managements for the slabs that will eventually hold slots that are 512 or
yes,
however many.
Yes.
by size.
Correct.
So it's the cache. So each type of cache only holds metadata about that type of slab.
Correct. So when we use the term slab here, we're talking about the literal page of memory that holds these slots for the object.
It can have more than one page, right?
So a slab can, but typically, if we're going to use the terminology correct, what we'll see. Let's sudo vm debug. So I'm going to use something called libslub. It is installed on the Dojo already. There are a couple things that are perpetual pain. If you try and do what I do, one, do not have pwn.debug in your .gdb. It will break libslub. Pwn.debug does its own weird nonsense with Python virtual environments, and it will break libslub. So do not have pwn.debug if you want to do what I'm about to do. So we can source. This is the same thing that you would do, like if you added it to your GDB init. I'm just going to do it at the command line. I want libslub, and I want libslub.py. Libslub is a cool project. When it comes to kernel tools or tools that do this type of stuff, they're kind of rare, and they also are prone to breakage. If we take a look here at the user guide, they have a command SB list, which is going to show the same thing that I just showed here, right? It's essentially catting proc all sims, or not proc tails, it's proc slab info. It's just giving us a way to see that from inside the debugger. What I'm interested in here to answer your kind of question about caches. And I could do this. Let's do that 512. I could do this from the debugger itself and find the pointers and cache them and dereference them. But libslub makes this way less pain because there's a lot of pointers you have to navigate inside. So if we look at the struct that represents a cache, again, this is the highest level data structure to think about. The cache itself holds metadata, which is what is the size of the objects that are supposed to be here. It also maintains a list of how many of those objects are in use, how many of those are allocated, how many of those are not. So the cache data structure is containing kind of metadata about how the slabs are used. Now, this particular cache has one slab in use that contains 8 objects, right? And so a cache is responsible for managing slabs. Well, let me see. I have a canned demo that will show this, but I'm going to see if I can find. Okay. One real quick here to demonstrate. That doesn't have. Oh, that's just like the main stuff. Are you going to show me? Look at this. Oh no. Don't fail me now, Dojo. What I was about to pump out here was there, or a cache is responsible for juggling multiple slabs, right? If we kind of hand wave and think that a slab is a page, the cache is responsible for keeping track of all of the pages that are being used for 512 byte allocations. Right? Because imagine that if we can only fit 8 to a page, there's probably more than 8 512 byte objects that need to get allocated by the kernel. Okay? And so we run into Okay. Okay. I'll take it. Right. I'll take a bounce that makes everything work. The cache is responsible not only for pointing to one slab that is the current slab that is in use, but also other slabs that it's not actively using, but are also slabs that are responsible for 512 byte objects. Does that make sense as far as what is the purpose of the cache?
Yeah.
Cool. A kind of interesting anecdote there is by default, which will be the case for everything in this channel or in this module, slabs that are full are not tracked by the cache. So we could envision that there's a page of memory that is a slab that is being used by the 512 byte cache. If that page of memory, that slab gets filled, right? We just allocated 8 things. Then the kernel, the cache, doesn't need to track it. We just say, oh, go be free. And then we get a new page of memory to be the slab that we're going to be working. Yes.
Well, once it's free, it gets tracked again. Right?
Yes. Once a single object is free from that page, it becomes tracked again. The terminology that we use would be a full page, a partial page, which is what I was going to show. A partial page is a page that has some free allocations or some free objects, some allocated objects, but is not the one that we're currently using.
If the cache is not tracking a full slab,
Mhm.
how does it know when an object gets free from that slab?
Well, somebody has to call free on one of those objects, right? And so by virtue of calling free on an object, this is now a page that I need to carry.
So it only starts tracking once a free is called, in
Mhm.
case that hasn't been tracked.
Yes, in the case of a fully allocated page or a fully allocated slab, when one of those objects is free, it is no longer a fully allocated slab, right? At which point it becomes a partial slab, would be the terminology that we would use. And inside the cache data structure, there is a linked list of partial slabs. And so when a full page has an object freed, that page gets added to the partial list inside the cache data structure.
And the partial list only holds pages, not slabs.
The correct terminology would be to say that it is a partial slab. In practice, a slab is a page. Now someone is going to come out and spike me for that statement because you can have allocations that are larger than a page, right? Like this gets a little silly when you start saying, okay, well, what if my objects are a page in size? Is every object a slab? Like things kind of fall apart at that moment. Okay. Let's see if things work for us here. We're going to source opt libslub libslub.py. And then we're going to yoink from the documentation. I need partial slab. So SB cache. I'm interested in, we were looking at, what was it, kmalloc 512. There's the cache, there's the cache CPU. There is one page in the partial list for this cache. So if I were to take, let's run times main slab. So what we see here is the difference between these two commands is the partial is pointing to E9980. This is a partial slab that can handle 8 objects, but only 7 are currently allocated.
As the frozen for what's left.
So this is, there's, I don't,
Or is one of them just frozen?
I'm going to ignore the frozen for now, right? We're just going to focus on whether something is allocated or not. And so 7 of the 8 are allocated, right? And that is in the partial, this partial slab, okay. But if I run this command and look at the main slab, the slab that we're currently working on, which is funny, is 8 of 8. And so it's currently fully in use. Okay, so we have this idea of there's this cache, it's responsible for managing slabs. Slabs contain objects. These objects can be these slots can either be allocated and contain an object or free, at which point they're not an object. Then, great. Now, one of the interesting things, you don't need to know this to solve the challenges, but it's worth noting, when we talk about performance being something that is important for the kernel, part of the reason that they use a slab allocator is because these slabs are not only for specific sizes. I happen to, and I did this somewhat on purpose, look at only the KMalloc 512, but we cache. But if we look at some of the names of these caches, some of these aren't just like some size, right? It turns out the kernel can have caches that are dedicated for a specific type of object. All right. And that makes some sense. An object is going to be the same size, right? It's going to be a constant size because it's all one type of object. So it makes sense to have a cache for the size of, I don't know, or something that makes some sense. Whatever. Some TCP thing, right? There's some TCP structure that the kernel is going to need to do TCP work. It's going to be something that's going to be allocating and deallocating a lot. So it makes sense to have a dedicated cache for that specific kernel object, right? Now, one of the other advantages here of this, of having a dedicated cache, is we can make assumptions about this region of memory that we can't do with like a libc implementation. We can pre-initialize every single slot with that object. Weird chase there, right? Like thinking about this, because if I'm using dynamic memory in userland, I allocate it and then I write the values that I need, right? But if the kernel has these objects that always have these default values, we can pre-write every single slot with the default initialized values for that object type. At which point, what does initialization of this dynamic object look like? I just get the pointer and then fix up the stuff that isn't default. So it is actually a faster form of allocation because these slots can have the default initialization done before you actually ask for it. That's one of the reasons why there's other people, but one of the reasons why you see these object-specific caches. All right, so that all hopefully makes some sense. Hopefully I'm using my terminology correctly. For a given type of object or size, there is a cache. Every cache holds slabs. Slabs consist of one or more pages. Slabs consist of a series of slots, and slots contain objects. Vocabulary. All right, this is hopefully a visual representation of what I just described. I'm kind of sidestepping this in the literal implementation. There is a difference between a K9 cache and a K9 cache CPU. You do not really need to deal with it. But you can think of it very similar to how the T-cache is an optimization for the CPU for a specific thread. The KMEM cache will have a KMEM cache CPU for every CPU. And what that is supposed to do is to reduce contention between multiple CPUs that are trying to allocate the same size at the same time, right? We don't have to put a lock on this page of memory because this CPU has this KMEM cache CPU, which points to one region of memory that this CPU is free to use. And then this CPU refers to this KMEM, or not KMEM, it'd be a separate KMEM cache CPU. That points to a different backing memory. So it's very similar to how the T-cache serves as a optimization so that there's less contention across threads or CPUs. There's a similar kind of mechanism here inside the kernel. You don't have to deal with it because, as I mentioned, the VM is single-threaded. So specifically to try and prevent that from being a problem for you, because this becomes much messier when you have multiple threads that are now interacting with these data structures. The other thing that I mistakenly identified here, KMEM cache node. So this is the implementation of the higher level cache that a particular CPU is using. This KMEM cache node holds all of the other like slab data that is not currently used. So if it's not something that is currently being used, then we hold the metadata over here. Again, you don't necessarily need to know it, but I think it's worth pointing out if you ever decide to go down the rabbit hole of this in GDP, is you will see this separation of the data structures here. All right, cool. I mentioned that there is a slab that is in use, right? This is the working slab. Slabs that, when a slab is filled, so we need a new slab, partial slabs will kind of slot in there. That's why we keep this list of partial slabs, which is what I was showing right up here. The slab that is currently in use, say, okay, but if we were to try and allocate something again, then we need to pull from the partial slab. And so we'll sub this guy in from the partial list down here to be the main slab, and this will become our working slab, right? Once it's filled, and we need to allocate something. Question from Twitch, would the challenges be a lot harder if there were multiple CPUs? The answer is yes. I think it would be a super cool thing to do. There are several things that are natural kind of extensions of the existing content. One would be to give you multiple CPUs in the VM, which would suddenly create a whole lot more contention. So like heap spraying becomes a much more very real problem, which we'll talk about the concept of heap spraying. But for Twitch, that becomes a much more necessary thing, and you can fail much more often. And then the other thing is, which we don't talk about here, within the context of this module, a page of memory is always used for a specific slab. And so we don't do, there's a whole class of attacks on the kernel heap that are cross-cache attacks. And we are hand waving that away as just like out of scope for this module. And so two things that would be super cool to expand on this would be multiple CPUs, because that would be more pain for you, and then cross-cache attacks, which would also be more pain for you. But this module as is pretty good. So these partial slabs are tracked in a linked list, which is the partial list inside the KMEM cache node. Full slabs aren't tracked at all, unless you specifically build the kernel with a setting to do that. Instead, we just set them free, and then when any of those objects are free, this is suddenly something that needs to be tracked in the partial list. We already saw that. There's a visual representation of what I was talking about here, where we have, in this case, I'm using 256 bytes. We have all these slots, which may or may not hold objects. These are all fixed sizes. Bam. this point somewhere. How do we deal with freed objects? Well, this works very similar to the Tcache. There is a singly linked list, which is referred to as the free list. The free list points to, that arrow technically should point to the beginning of the allocation. But it points to a freed slot. As we free more things, what do? We push. There's one gotcha here. You saw slides. What's the gotcha? You didn't see the slides.
That sometimes it's random.
No, we aren't in that deck yet. This is just how it works normally. How it works normally, there's a gotcha. So on the Tcache, the next pointer is at the beginning of the allocation. This one is in the middle. Let's see here, right there. 2 slides ahead. The free slot, in the free slots, the next pointer is not at the beginning of the free slot. Instead, it is literally whatever the size of the memory is divided by 2. It's going to be in the middle. You're like, that's weird. Why do you think that is a good thing? It's actually a good thing. What does it reduce? It reduces the very thing that we're trying to do. We're trying to, like, when we exploit things, we try and corrupt metadata, right? It's kind of silly putting the metadata at the very beginning. So that means, like, it off by 1 byte, right? I write 1 more byte, I've corrupted metadata. If we hide the next pointer in the middle of this free space, okay, well, maybe if some kernel dev, did something silly and they're off by 1 and they overwrite the beginning bytes here, did they screw up any of the metadata? No. Right? And so it reduces the likelihood of there being corruption. Right?
So what does the start space hold?
Nothing. It's just whatever.
It's just empty.
You're saying what is in this initial space here before the pointer?
Yeah.
Whatever happened to be there.
I'm assuming the object holds like some type of data.
Yeah.
So if the pointer to the next object is, oh, this is a free.
This is a free type.
Yeah.
So when it's free, whatever is in the first half is whatever was in the first half when it was allocated, right? There's no reason for us to mess with it. The only thing that gets overwritten when free, hand waving for people, it is the next pointer here that is in the middle of that free slot. Cool. Yeah, Twitch correctly points out it reduces our ability to hack, kind of, sort of. It turns out dividing the size by 2 is really hard. Right? So for something that is hex 100, the next pointer would be hex 80. I know it's hex, so the division is hard, but that is how it works. I saw the and so we can pretty easily find where these next pointers are. All right. There are private caches, right? As I pointed out, these are for specific objects. To create a private cache, the kernel function is kernel cache alloc, which creates a cache. The first several, I want to say 4 or 5 levels of this module, in an effort to, again, make things simpler, these challenges create their own cache. And you are the only thing that interacts with that cache, right? So that way, hopefully, it's easier for you to reason about what is going on in these slots and with this memory. Okay. Now, we said this free list is a singly linked list. It turns out libslub can help us out there. There's this nice little show free list. So let's see if we can do, no, what is the correct, what are you grumpy about? Oh, that one is empty. That makes sense. Let's, but I'll show you in the canned demo that I have. Because I can force this list to contain a bunch of objects so that I can show it to you, instead of just like betting that a particular slab is in a state. Okay. Yeah, we did that. We did that. Bam, bam, bam. So there are private caches. That's how you make them. And then there are these general purpose caches, which is what I was just looking at, right? Came out 512. This does not talk about the CG. I'm going to assume it's in another slide deck. So we'll have them. Is it? Ah, bam. So I keep talking about like kernel objects, right? What is a kernel object? Like, when is a kernel object created?
The kernel makes them.
Right, the kernel makes them. Sure. Can we make the kernel need to make something? And when do we do that? Right? I'm going to ask this like really deep question, and I think it's really cool to see we pull all the way back to something as simple as this. If I am on the terminal and I do echo hello, did the kernel need to like deal with dynamic memory here?
Say no.
Say no?
I think no.
So we called echo. Then there's this bar in the middle. What's the bar in the middle? But how do pipes work? I'm not saying like write me an implementation of a pipe, right? But like, how is a pipe created?
Just the communication between one process and another.
Right? Well, I'm not saying that with 100% certainty this is what Bash does, right? But the concept we can trace it to see. But the concept of a pipe boils down to this syscall pipe, right? What's a syscall? Who do we talk to when we make a syscall? The kernel. Oh, when I have a pipe, what do? I'm writing bytes into this concept of a pipe. Does that pipe need to be backed by memory? Yeah. Like at the end of the day, there's disk, there's memory, and there's register. We don't really have that many things to play around with, right? We can think of it from user land. So, oh yeah, man, there's like this pipe, and Mario goes down it. He plugs along, and he comes out in the dungeon level, and there's turtles. It's super cool, right? And I like that attraction. But when we get down to the nitty gritty, what does a pipe have to be? Some region of memory and a couple pointers that are tracking what bytes matter. We've seen this kind of idea when we looked at how file structs work, right? There's a region of memory, there's a bunch of pointers, and we're just like, we're making the lie work. With file structs, we're doing it with a buffer. With a pipe, it's the same thing. There is some buffer of memory that the kernel is managing that is responsible for holding this data. So something as simple as creating a pipe, suddenly the kernel needs memory. And it needs it on demand, and it doesn't know how long it's going to need it, right? I could make a pipe and I could need it for 3 days. I could make a pipe and be done with it in 2 minutes or 3 seconds. So this is a dynamic region of memory that has to be created by the kernel to facilitate the action of a pipe. And this is true not just for pipes, but for tons of things that we take for granted from user. So the answer is yes, we absolutely can force the kernel to kind of create this dynamic memory. Now, some kernel objects are like pipe, where they hold user data. Do we trust user data as the kernel? No. We think users are stupid. And that's because 9 times out of 10 they are. And I am a user of the kernel. I am stupid. Right? This isn't a dig on anyone else. The kernel should not trust me. I do not know what I'm doing. And the kernel doesn't trust me. That is the difference between the kmalloc, this is 8K cache, and the kmalloc CG 8K cache. The CG is for untrusted user data. Right? So that what that means is that the kernel can put sensitive stuff that could be corrupted in KMalc 8K. If it's something that is not sensitive, and it's something that takes user data, then it will use this KMalc CG 8K. And it's again another separation of trying to keep sensitive stuff inside the kernel away from dirty memory that the user has somehow been able to touch. Cool. All right. Any questions about like the high level implementation of Slab? Cool. The first like 4 or 5 levels of this module all play around with that concept, except we turn on additional protections, which is what we're going to speed run through right here. The first is tree list randomization. So by default, like in level 1, when you allocate, when the kernel allocates something from a slab, you're going to get the first object in the page, then you're going to get the next object in the page, et cetera, right? So we can deterministically know the order of these allocations. But with randomization, what happens is the cache for every slab will have a random order that these slots will get returned. And so this eliminates our ability from a fresh slab to know which slots will be returned. It turns out this really isn't that big of a deal. There was kind of this initial shocking, oh my gosh, this is going to be hard. It's not really that crazy. This works for newly created slabs, right? However, we have to deal with the realities of a data structure. How does a singly linked list work? Push to the head, and then we shovel everything back. And so it's great that the kernel can randomize the order for a new slab. The kernel really has no control over a slab that's fully in use, right? And so you can, no matter what the random setup is, you can create a kind of deterministic setup by freeing things and setting up the free list in whatever order you want, because that is how that data structure works. Okay. So imagine a use after free scenario. We have a pointer to the first slot here in the slab, and there is a next pointer that points to the immediately next slot. We could just clobber that, right? Do the same thing we do in the Tcache. This isn't anything fancy. Well, it turns out, very, very much like safe linking, there is another fun XOR mechanic. And this one sounds way worse than it is. It is called tree list hardening, right? It's the same concept of safe linking. We need to mess up the next pointer, so that way you can't just leak it out and know where things are in memory. Safe linking used 2 values, right? The address of the pointer and then the pointer itself. Tree list hardening uses 3 values. It uses the pointer, the address of the pointer, and a random value that is specific to the cache. So this should be like much harder for an attacker to reason about. All right. I don't think I mentioned this in the pre-recording. Slab just reverses the order of bytes. Okay. Just some people fixate on Slab. You don't need to. And the reason you don't need to, yeah, whatever, it's encoded. Yep. Cool. The reason you don't need to is this is the scenario that can happen. But what if that pointer, instead of it being a valid, there's only one entry in the free list? You end up with this scenario. So I get the thing that I can read is the address of the pointer XORed with null, because the pointer is null, because it's the last thing in the free list, the only thing in the free list. So the pointer to the next thing is null, and then it's XORed with this random value. What have I obtained here? I have obtained
Address, pointer, and random. So
yes, which is all I need to decode any of these mangled values. So the trick here to get around this hardened tree list is to create the scenario so that there's one object or one slot in the free list. which means the next pointer will be null. And when I read that value, that gives me the thing that I need to XOR. Because if I take this value, that is the address of the pointer, XORed with null, XORed with random. So we end up with, and it's swab of address of pointer, but we don't have to worry about swab. All right. If we get that value, then we can take what we have leaked, XOR with the value where there is a pointer, and we end up with point. Make sense? Like it looks way crazier than it is. I promise you, right? Make the scenario to where there is one item in the phrase. Leak the mangled nonsense. Because this mangled nonsense is stuff that I don't have control over, XORed with null. I can then take that thing that I've leaked, XOR where there is a valid pointer, and what I get is the valid pointer. So what we take advantage of is the edge case where the pointer value is null. That is our kind of trick here. And if we control the cache, which you do for the first 5 levels, right? There's one dedicated cache. You're the only one that messes with it. That means that you have control over this free list. I can allocate things and I can free things. Okay? So you can pretty trivially create these scenarios. All right. Yep. The last thing that is worth touching on is I said that the kernel doesn't trust users, right? And so the kernel needs to try and sanity check whatever crazy stuff the user is doing to kernel memory. We typically see this via these 2 commands inside the kernel. You probably saw these way back when in like 466 at some point, when we had kernel modules made even in micromerge. But the way data is moved from user lane to the kernel or back is specifically via these functions, copy to user and copy from user. They aren't particularly interesting functions because they work almost identical to mem copy, right? So why do we have these dedicated copy to user and copy from? It's to ensure that if there is a kernel object that has some region of memory that is user writable, that the user doesn't go out of bounds. And this is something that's called a hardened user copy. What happens if the kernel accidentally copies and writes user data beyond this controlled region? We want to prevent that scenario. And so inside the cache, and remember the cache is the high-level kind of management data structure of this thing. For a specific object, there is going to be some region of memory inside that object that is user writable. Right? We can envision, for instance, with a pipe object. I don't know that this is true for a pipe object, but we can pretend that the pipe object has some pointers, and then there's the user data, right? The stuff that you ran into the pipe. Do I want the user to be able to write enough data to overwrite these pointers inside the pipe? No, right? So the object itself contains a region of memory that can contain user data. And then there's another region of memory that the user data should never be able to touch. And so this can be specified inside the cache. And it's specified by key value, it's specified by an offset, and then a size. If this is my object inside the kernel, the offset is the distance from the start of the object, at which point users are allowed to copy to and from. The size plus the offset is the end of the region that can be copied to and from usually kernel. Cool? And so in a hypothetical pipe scenario, the pipe pointers could be back here, the pipe pointers could be back here. We will never be able to, from copy to user and copy from user, joint bytes out of this object other than what is in this approved region for the cache. So these values are inside the cache. And if we were to look at the implementation of, where is it? Copy to user and copy from user, you'll see that there is a sanity check. You can do this on your own. There is a sanity check in the implementation of these functions where they look at the kmem cache to see if there is a offset in size. And if so, it enforces it. If there is not, then there's nothing to enforce. So YOLO. Lastly, KASLR. I think you've seen that. There's not anything super crazy there. One way that you can kind of break KASLR is with an oops. Know what oops is? This is the correct term. I didn't make it up. A kernel oops. Huh? Maybe you've done this. Have you caused a bad stuff to happen inside the kernel, and then you type dmessage and you get that little stack trace, and maybe it shows your RSP, tell you some registers, and says, hey, man, something bad happened. That's a kernel use, right? The kernel needs to be robust, not only in the sense of the literal implementation of the heap being different, but sometimes bad stuff will happen in the kernel, right? Kernel devs aren't perfect. Kernel driver writers aren't perfect. If the kernel makes a mistake, there's kind of three things that can happen. If the kernel is configured such that it will oops, which most of these are, then you can cause an error. And if the kernel is capable of kind of rolling back and recovering from it, it will. And if oops is enabled, these oops messages, then you can type dmessage, and dmessage will leak out some information. Right? The kernel says, hey, man, bad stuff happened. Here's what I can tell you. But don't worry, I recovered. That's an oops. If oopses are not enabled, then you can panic on oops. And that is when the kernel just locks up and it's your SOL, right? The kernel says, we have zero tolerance for any of this nonsense, and it will lock up. There are challenges here where panic on oops is the case. That means if you do your heap stuff wrong and you cause it to crash, the entire kernel locks up and you have to restart the VM. One of the reasons people enjoy this module. Somebody on Twitch here who is a kernel lover says that they think that when they tackled this module last year, they made the kernel panic 1,000 times. That sounds like a really good time. Instead of doing that, maybe we could use GDB, think about what we're doing. But if you want to YOLO and crash 1,000 times, that's your call. With the long VM startup times, that can be a source of pain. With that, we'll take a short break. Hit the last slide, touch our demo, call it good. Questions, comments before I...
One question.
Yes.
So the cache holds metadata about how much offset and the size of what can be copied.
Yes.
Does that mean that if it's a general purpose cache and
So right here,
right,
there's a general purpose cache.
if it's a general purpose cache and it's, for example, one slab is is allocating some type of object, another slab of the same cache is allocating another type of object, but the objects have different user data sizes. How does it account for that?
So I looked at KMalloc 512, right? Which is, does this one deal with user data or no?
No.
Cool. So what is the offset for this 512 byte object?
Excellent.
Which is?
Half of it.
Is it?
Can't do that.
Can I print hex 512?
Well, kind of almost.
Okay. That's interesting.
Isn't hex 100 256?
Okay. So apparently that is how this bad boy rolled. I wouldn't have expected that. The one that we should be interested in is the KMalloc CG. Same thing. Apparently, just don't touch the first. I'm not entirely sure why, but I'll take it. Right, we just have to trust what we see.
Yeah, but my question was, if we have two different slabs holding two different objects from the same cache, and the cache has only one offset and one size,
Then all of the objects must conform to this rule.
even if it's a general purpose cache, what if one object
This is a general
that bottom of
the CG, yeah, that's a general purpose cache. That can take user data. There's our offset, there's our size. Them's the rules. Them's the breaks.
it doesn't matter what type of data the object is allocating or using.
Well, this is not. This is kind of bait because I know this particular kernel is not compiled like this particular challenge. Each of these challenges actually have a different kernel. We have to actually rebuild the kernel. These are build time options when you build the kernel. These things like hardened free list or hardened user copy. All right, I think that's so. So I know this kernel that we're looking at right now does not have hardened user copy. So this could just all be made up nonsense. But these are the values that would be enforced for the cache, period. Now, since this isn't built with hardened user copy, these values don't actually get enforced. But these are the values. If I were to start another kernel, maybe it would show something different. I have put that off to be quite honest. But those are the little values that matter. One thing that is worth noting. Copy from user, copy to user is what's supposed to happen. There are a few edge cases in the kernel where they don't follow the rules, right? The rules are supposed to be, if we're moving data from the kernel to userland, we will always use copy from user, copy to user, and it will always do the sanity check. There are places in the kernel where that is not necessarily the case. And if I'm not calling these functions, which do the balance checks, do the balance checks matter? No, they do not. Somebody says I should show pt dump. Okay. You can do that. Boom, source opt pt dump pt.py, and then we type pt. So you remember VM-map, right? Our good friend VM-map. PT is the page tables. It's very similar to VM-map, except now we get to see everything because we're inside the kernel, right? And so we get to see all memory. When we type VM-map, we only get to see this stuff here up at the top that's in user space. But when we use PT, we can suddenly see these other regions of memory. So like, we probably have dealt with FizzMap at some point. Cool, now we can see where in memory is FizzMap. Those are all virtual memory allocations. And then if we fire all the way down here to the bottom, makes sense, because kernel memory is, again, the absolute the highest in sec. We see this is the rigid memory that is the kernel itself. The executable memory of the kernel is this. Oh, yeah, you got it. That guy right there. This is the kernel's executable memory. These challenges utilize a kernel module for you to cause, for instance, KML to occur. It's an implementation detail, very similar to kind of what we saw with MicroArch or the kernel security module. There is a kernel module that allows you to kind of more simply cause the kernel to do different things. This is the location in memory where the kernel module's executable memory is located. And so we can use PT to get a quick jump out there to kind of reason about what's going on. Also a cool tool. Twitch says they really liked PT. They just won't use GDB, man. I preach GDB. All right. So some people just refuse to learn. But with that, we'll take a quick break here. We'll come back, hit the last slide, look at a quick demo, and call it good. All right. We're back. Last slide. Speed run it. Oh no, what did I hit? I hit some button. Cool. So if that's how the kernel heap works, and that is some of the like security mechanisms that can be built into the kernel, why does any of this matter, right? When we talk about kernel exploitation. Well, when we think about the kernel itself, from user land, there's not a lot of ways for us to interact with the kernel, right? You're not going to, in the kernel security module of 466, we have this kernel module and we're like, it's just going to run shellcode. That's not a same thing that you're going to just find in a normal Linux kernel. Instead, the only thing that you really get to do from user land is perform syscalls. And the primary thing that you get to interact with in the kernel is, in fact, the heap. And so you have to cause a vulnerability to occur from user land by calling syscalls, which forces the kernel to interact with this heap implementation. And since we are interacting with a heap, the same kind of takeaways that we had from learning about how the glibc heap works apply, right? Well, there may be some more rules to it, may have to tinker or approach a little bit, but things like buffer overflows or reading out of bounds that still exists. Use after free. If I somehow manage to get a pointer, that still exists. Corrupting metadata, like a next pointer and the tcache, or in this case, the free list of the kernel. This concept still exists, as does the idea of having an arbitrary read or arbitrary write primitive. Okay? It's just that the way that we start is now by performing syscalls to force the heap to do something. For the record, the first like 4 or 5 levels utilize a kernel module that is going to just happily let you perform this ioctl, and we will call cout. So you don't have to think about, what do you mean perform a syscall? But in reality, you don't have, every Linux system doesn't have this happy kernel module that's just like, what do you want to allocate, right? And so when we think about exploitation, we think about, as far as like the deeper, more real kernel exploitation, it's how do we cause these behaviors to occur? Now, one of the problems with the heap, which I alluded to a little bit ago when somebody asked on Twitch, is we have these slabs, and these slabs can be used by multiple CPUs, right? And we aren't the only, even if there is only one CPU, which is the case for this VM, this module, am I the only process that is going to call in the kernel? Like, and I guaranteed if I run my process that everything I do is the only thing that will happen, even though there's one CPU. Do I have that guarantee? Why or why not?
CPU, there's a lot going on in the background.
So, but what is the background if there's one CPU? What do you mean? You have the right idea, but why? I run my process is going to allocate 30 things. Do I have a guarantee that 30 things were allocated consecutively only by me? Why or why not?
Other process can also take the CPU.
An other process could take over the CPU. What is that? What's that mechanism?
Context switch?
Yes, context switching, right? So even when there's only one CPU, and so we're reducing the amount of things that could be going on simultaneously, that one CPU, your process could still get context switched to whatever else is running on that system. And anything else that's running on the system can interact with that same slab. So that means that we are really deterministic, even when we have one CPU. Because we could, at any point, we could get context switch, and some other process may cause the kernel to create an object that is going to be allocated from that slab. And that means that we kind of end up in this like undetermined state when we think about what is the state of a slab. And there may be one object that is particularly interesting. This is the object that I want to corrupt, or this is the object that has the flag, right? How do I get to this if I don't know which slot it is, and I also don't know what slots are in use and which ones aren't. Right? This is a problem. So the way that we get around this is something that's called heap spraying. The attacker will try and allocate an object. It will exist somewhere. It may or may not be near the target object. What the attacker wants to do is create an attacker object that is, I think the terminology I always use is wrong, but is physically located, right? It's not physics because it's called virtual memory, but I want to create an attacker object that is near my target, right? Having an allocation up here doesn't help me. The thing that I'm interested in is too far away. So the attacker strategy is to spray, which means that we're going to fill this slab with stuff that I control. Now, there's still slots here that I don't control, but it improves my odds, right? Now, I'll go through the slides and then I'll circle back. So by spraying the heap, I improve the odds that I have an object that is near my target thing. So what I want to do is I want to create a scenario that's like this, where there is a slab where majority of the objects, if not all of them, are attacker-controlled objects. So now when there should be a cool slide. If I were revise this, there would be a slide where, boop, we have target object and it shows up right here, right? Now, one of the things to think about here is if I start from this state right here, an attacker could allocate, 1, 2, 3, 4, 5, 6 things. The attacker could then free one of these things, which means I know there is one free slot, and then hopefully be able to force the target allocation to occur, which would then fill the one empty slot. The problem here is, does that guarantee the attacker a good state? I specifically made this one so that it isn't, right? The attacker could fill all of these, the attacker could free one, and then cause the target allocation. Is the attacker right next to the allocation here? No. So instead, what a smart attacker would do is they would allocate not just enough to fill whatever the current state of thing is. And once I fill the current thing and I allocate another, what do I get? Where do new slabs come from first? Where's the first place new slabs come from? Partials. So I would probably want to, if I'm a savvy attacker, I want to allocate to fill the active slab. I want to allocate to fill the partial slab and the next partial slab, and however many partial slabs there are, because what is my ideal state? It's empty, and then I fill it with all of mine. So every object is an attacker control object. And then as you pointed out here, I free one of them, at which point now I've guaranteed that that target allocation will be next to something I control.
Don't know which object.
You're right. That's a different problem, right? So the first problem the attacker has is how do I get an attacker control object next to my target object? Okay. If all of these were attacker objects and there's one target object, you're correct. I don't know which attacker object is next to the target object, but I've at least gotten one of them next to it. Okay? And this is part of the problem of heap spraying, right? The thing that you pointed out is part of the problem because we don't have insight there. Now, where I said target objects, what is a target object? In the first few levels of this module, it's pretty obvious. We put something that you definitely want and clearly want there. But in the later couple challenges, and in the kind of more general kernel exploitation context, there are specific kernel objects that are very commonly utilized when you talk about kernel exploitation or kernel heap exploitation. Because these general use caches can hold many different kinds of objects, right? And those general use caches are used by all processes, and we can cause that by performing syscalls. But not all kernel objects are created equal. There are things that we are interested in, particularly if there is a kernel object that we can create that is flexible in how big it is. What if there is a magic kernel object that we could cause the kernel to make, but sometimes it's 512, but maybe if I want to go mess around with the 256 byte cache, I'll just make a 256 byte version of this object, right? A variable size kernel object. That'd be super cool, right? Turns out there are some kernel objects that are user controllable as far as the size of the object, which allows us to specifically target specific caches. Okay. What if there's an object that specifically doesn't follow the rules of copy to user or copy from user? That is something I would be interested in, right? Because then I don't have to worry about the pardon user copy. And lastly, object pointers are function pointers, right? The kernel, for the most part, expects the kernel to behave correctly, which means that there are function pointers inside some of these kernel objects. And so if we think about just heap corruption, if I can corrupt a object pointer, that can give me a arbitrary read, arbitrary write, depending upon how that pointer is being used. And if I can corrupt a function pointer inside an object, well, that gives me the opportunity to kind of get arbitrary execution because I can call into whatever I want. So there's two objects in particular that are worth mentioning, and they are used in the later challenges of the module. The first is message message, which I have a nice little demo that I can run through. And then the second one is pipe buffer, which, as you could imagine, is the buffer for a pipe. Right? Why are these interesting? So I think I talked a little bit about message message, probably off stream. But in Windows, we talked about, yeah, it was you. It was you. We talked about message queues on Windows for something. I don't remember why. The message queue for impersonation. For impersonation on a pipe, the MSDN on Windows says that it will impersonate the process that the most recent message on the pipe was read from. And the question, this was, I think, off stream. But that was the terminology when I was off stream talking about how impersonation works. And the question was, what the heck is a message? Right? And in this concept of a message exists abstractly, and it's not a crazy idea. That what if this pipe isn't just a arbitrary stream of bytes, but there are atomic chunks, right, that are well defined and well structured. Now in Windows, you can create a pipe and have it be a message, make it be consumed at a message level, right? So it's read in chunks of known sizes. On Linux, you don't really have that. Instead, we have this IPC mechanism that is messaging, right? This is where this message concept comes in. And the man page here, man7mq overview. It'll give us a nice high-level view of this idea. It's really not that crazy. What we do is we define let's see if it says it here. If not, I know it says it in another man page. Okay. So we define it doesn't. We define a struct that is a message, right? And a message is not a oh no. Okay. A message is not a crazy data structure. It is literally just a long followed by an arbitrary number of bytes. Right? In this case, they say one, but we can define this as a buffer of 256 bytes, whatever, just some constant size. This long is there to indicate the type of message, because you could envision that there are good messages and in this queue, because it's a pipe is a queue, right? And so when I'm consuming messages, I want to check the type. That informs me of how to interpret the arbitrary number of bytes that are active. So I define this message buff struct. I then use message send to send a message, and I use message receive to receive a message. Now there is a little bit of ritual as far as creating this queue or defining that this queue exists, where I have to create a queue ID so that two different processes can refer to the same queue. But it's very similar to a pipe. We have a nice, pretty demo here. A message. So we'll take a quick look at writer, not the binary, the C program. As you can see, it's particularly crazy. I don't care about this. I am defining a message buff. In this case, I'm actually not using this cache size, so whatever. But I'm defining a message buff as type followed by 100 bytes. I am copying to message hello world. We're going to block before creating these messages. I'm going to loop 20 times, and I am going to send the message to the queue. Where you're like, okay, where did this queue come from?
Yeah.
Uh,
I need to find out the.
I'm defining it right here. This is creating a token, which is kind of a silly thing, but we can. You're converting a path, and I'm just using the current directory, to a token, which is a unique identifier for IPC. It's not literally a path. It's kind of like how Windows has the kind of global everything is an object hidden thing. There are a few mechanisms on Linux where everything is a file except for these other things that aren't. Right? Like you can probably get to them via some kind of file, but the literal name is a file path, except that it really isn't, in the sense that you can't just like ls it and see it. And so what I'm doing here is I am defining a, where's my queue?
It's under the circle.
Your copy. Right. So the this is an array of ints of QIDs. I then create the QIDs by calling message get with the token of the current directory followed by a number. Right. I'm just looping, so I'm creating a bunch of queues. And then sending the messages down all of these queues. I could have created, in hindsight, I could have pulled this out and just had one queue and then wrote all of them to the same queue. I don't know why I didn't. And that's what you get.
I'm also changing the type of the message buffer every time.
Yes, and I'm doing that for demonstrative purposes so that we can see on the reader side that it's reading all of these.
Does the type hold any value? Like if you just make it any random things?
So the rule, if we were to parse the man page, is that the type ID must be a positive number. It must be greater than 0.
Oh, it's an ID.
So no. So there's two different things going on here. Okay? There is the message queue, which is my bad for throwing this demo together. There's the message queue, which for whatever reason I'm creating 20 here, right? The message queue is equivalent to a pipe. So for whatever reason I'm creating 20 different pipes. Then there is the type of this message buff struct. This type value, the man page specifications that the long value must be greater than 0, unless it's like an error, like something horrific happened. And the meaning of this type value is entirely application dependent, right? So I could say that 1 is hello world, 2 is a struct that represents a person structure, right? Because the contents of this arbitrary array is up for whatever user interpretation I want. And so the concept here, or how this like would more correctly be used by a normal program, is we would not do this. Instead, we would have one queue, right?
You want to change the I until.
Did I leave an I in there?
Yeah, but then.
Happen. Cool. So I have one queue. I have queue 0, right? And I'm creating the queue right here. I'm storing it in this array for whatever stupid reason. And then I am looping and sending 20 messages down this queue. On the reader side, let's do the opposite. I have to fix up the code here as well, so I'm not looping through an arbitrary number. Yeah. On the reader side, I'm doing essentially the same thing, since both of these programs are going to be in the same directory. .0 is going to refer to the same thing, same location when I tokenize, which means they both are going to get the same message queue. And that should probably be not I, but 0. Plug in the Mac. One thing I like about this room, all right, the AC may not be good, but it does have convenient power out. So we create this message queue, and then on the reader side, I'm still looping. I'm reading from this queue, and then I'm just printing out what I interpret when I parse these messages. Right. So on the user, on the way that you would use this in your application, if you have multiple processes, or how this is meant to be used for IPC, is both the reader and the writer refer to the same single queue. However, there may be multiple types of messages, right? Maybe I write something that is just a status update. There's something that is like an edit instruction. There's something that's like an error has occurred. I would encode the meaning of these messages by whatever the arbitrary encoding that I choose as a user application in this type long. And then on the user application level, I check this type, and that tells me how to parse whatever this second value is. I can parse it as a struct, I can parse it as a string. That's however I decide to run my application. And so this concept of a message queue allows me to pass structured data over a queue, opposed to a pipe, which is an arbitrary stream of bytes. Right? Now we can have structured reads from pipe in the sense that we read until a new line and we do that, but we're essentially defining our own message structure when we do that. Okay? We're using message as IPC allows us to do this in a more formal and well-structured, well-defined manner. So I'm not going to compile this yet. Instead, I'm going to run the demo as is, just in case the edits cause the demo to explode. It's cool if it does, but I want to show it actually working first. So we'll run reader, where before reading messages, I hit enter, and apparently it doesn't block. Let's go into kernel message. Let's run writer. We'll run reader. And now we get those messages. We read. Okay, and so it's a way of doing IPC. Does this block now? Okay, now it blocks. I think. Oh, I know why. Because when just as an aside, when the reader creates the message get here, I'm just creating this with the key and then permissions. But when the writer does it, we specify IPC create. And so what was happening when I ran the reader first is the reader trying to read something that didn't exist, which is why it's just like, yeah, whatever, here's some bytes. Here's some nonsense. But once the writer has created the message queue, the reader will block on it correctly. All right, so now we're blocked there. We run writer, and the reader gets the messages. Make sense? All right, let's see if the edit so that there's a single queue behaves as one would expect. GCCO reader, reader.c, GCCO writer, writer.c. We'll run writer. We'll run reader. And we see it still works. What we changed is that this is all reading from one queue. This is all writing to one queue instead of the stupid that I had before, where I was creating a single message down 20 different queues. Say same effect, but that is how that is supposed to be used, right? So why is message interesting? Well, what did I get to control as a user here?
Size of the message.
Yes, I got to control the size of this message buffer. So what is that doing inside the kernel? Because this is getting, these messages are IPC. So this, when I do send message, the kernel has to create a heap object that is going to hold my message data. And then when I read over here, I'm doing this syscall into the kernel and say, kernel, give me that message data. The size of this allocation is something I control as a user. So that allows me to specifically target certain caches through the use of message. The way that this is defined inside the kernel, which you can follow here, is they define the message struct, and then they leave the end of the struct to be appended with the actual contents. So the object is whatever metadata followed by whatever the actual message is. And we see that the size of the message is defined in the metadata. And so this is kind of a arbitrarily defined kernel object. Message is the cause of a lot of silly, if you do the Googles. Right? And so that is a very interesting kernel object to influence the kernel heap. Let's take this message guy. We're still inside the VM over here, maybe. What I want to do is to the list. Oop. I want KMalloc CG. What do I want? K. M. What's my P? See if I can read. You know what I want? There we go. If I can type. So what I'm going to do here is I'm going to use GDB on the kernel to list KMalloc CG so that we can see the number of objects and get some of this metadata before I run my message writer. Okay, so this is before I do anything. We're going to go into kernel message. We still have our writer. Run our writer. We've created the messages. Take a look here. How big did I make these? That was a silly number.
Probably 96.
Do you see it? 42. No.
64.
64, 384.
Are we looking for option like first column to change.
Yeah, so I should see that the number of objects,
No.
change. This is what I get for carving up the demo. Use 64.
Well, in use of some of them have changed. Not just the object.
Yeah. That's I'm sorry. That is what I'm looking at.
It is 128 because it goes from 36 to 56. That's 20.
It should be a difference of roughly 20. 128, 36. Yeah. All right. I can't read. So you're good. So what we saw here was the 128 went from 36 before to 56 now. And that our theory here is that those are the messages. Are those still there?
Should be.
Why? My writer process is ended. Are they still there? Why?
I'm not sure if the kernel cleaned that up or not. They should be there.
They should be there? Why do you think that?
Because they were never free. Yeah. Or if something freed them, we don't.
Well, what is the functionality of message? It's for IPC, right? Interprocess communication. So if this is for communicating across processes, could somebody try and read these messages later?
I don't think that's an intended being.
Yeah. You don't think so?
If it's cross processes, the process already died. So
Where am I here? We'll continue here. Oh no, did my VM die?
oops.
Did I? No, but if I oopsed, I should recover here.
Kernel empty.
Continue. Well, did that make it? I'm just going to say, okay. I'm going to run reader. We are able to get all of them, right? And it makes sense because we wrote them to the queue. The queue exists beyond the lifespan of the writer process. I have now read them, which means that when I look at that list again, we should see, you said it was 128?
Where's the best?
Did I? What happened? We went from like 36 to 56, and now we're at 38. Is that right? That's the right numbers, right?
Well, the objects still exist though. It should be 56.
No, they don't. I consume them.
Oh, okay.
All right. So right here, well, what I did was I ran writer. That made it go from 36 to 56, which is a difference of 12. I then, whatever reason, locked up my terminal. Okay. And we somehow got that squared away. And I ran reader. This is reader consuming those from calling message read. The act of consuming them is that the kernel no longer needs to have those allocated, right? We pass the messages to the reader. So those have been free. So we see that number go back down, except we didn't end up at exactly 36. Why? I did this in the pre-recorded. I want to say I did a demo very similar to this, and it did work out exactly. I don't believe the demo is cursed, but what happened here? Is this 128 a general purpose? Am I the only one that touches it? No. So just in that little me messing about, something else happened, and the kernel was like, yeah, man, that guy needs the 128. And so now this doesn't map exactly 2020. Just to show that like what I'm talking about is real and you will experience this. All right, so now we have that and we freed that. What I should be able to do now is run SB cache and get the free list. And I get these on the main slab. Oh, that's because we were on 128. Okay, that works for me. So the free list on this slab has two allocations, two free slots. Okay. We said that the next pointers are not located at the beginning. Where are they located? In the middle. So where do I want to look at? I want to prove that there's the next pointer here that points to this one. What do I want to look at?
Plus 40 or half of it, or 80 for 2.
You want
I think it's 40. That's what.
hex 40?
So
Okay. Sometimes I don't math. I don't look at it like if you guys can math it faster, you're the math. And so that's half of the 128. Which is how we see that is the pointer that is written midway through the prior. There is also the ability, I have to refer to the actual docs here, where you can dump out -x with SB object. SB object followed by the address. I don't know. Isn't there a context on this? Yeah. I can dump the slot. There's another command that lets me, I don't remember it offhand, that lets me dump out. It is just -c, so it's not -x. This will let me say, I want to know what 3 objects are within the context of 4 from this object. And in this case, these are right next to each other. This is the one that I asked about. This is the end of the freed region. So this gives me an idea of what I could run, right? This is the thing that I'm interested in, this thing that I was interested in, or this is my target object that I'm in this set. Now, this didn't, can I? There we go. I can combine that. That's what I wanted to do. Now I can dump out both objects with the full bytes. These are right next to each other. These are both free. And we can see within that the midpoint of the object has that pointer. So we can fully visualize what's going on here with our slots using SB or using libslub, in this case with SB object. You can do all of these things with just GDB and raw casting. Your starting point is kmem cache, which is just a pointer to an arbitrary cache to begin with. The caches themselves have linked lists between caches. And so we can, and this is somewhat nice, this is what everybody did. Oops. This is what everybody had to do last year. Struct kmem cache star, and then we would dereference it. Oh, I'm missing a K. And I don't know why it's not green. But we would work from here, and then we would navigate these nodes to find the cache, and then we would read the metadata to find it, and we would go from the Kmin cache to the Kmin cache CPU to the slab. You can do all of this from raw GDB. I think it's a good time. Maybe some other people would disagree, but I think that's just worth pointing out because this is super cool, right? That we can do this, but I think it's also worth noting that the raw what it's doing under the hood here isn't magic. It's just navigating this in an automated fashion, and that's just a global pointer that came in cache. All right, questions, comments, concerns there? All right. The last thing that is worth discussing, I have time, is this thing called mod probe path. So mod probe path has been around forever. My question to you is when I do bin cat, how does the kernel know what to do? Okay, so it's gonna be like, okay, what is this? All right, cool. It's an elf. The kernel's gonna be like, all right, cool, this is an elf. Do I know what to do with elves? Answer is I hope so, because like elves are super common, right? And so the kernel knows this is an elf. We deal with elves by starting up the loader. We load the elf into memory and we fire off, right? We go through kind of our binary startup process that Jan has an amazing lecture on. Well, what about if I do, there's always a do.py, right? I do do.py. How does the kernel know what to do?
It's the shebang and
Right. So we can't just say, oh, well, this is ASCII. You clearly need to use Python, right? Instead, we look at the shebang. And the shebang informs the kernel of what to use to run, how to interpret this particular text. Now, what about other binaries? Like if I, it's cat dev random into my cool bin. All right. And then we chmod plus x my cool bin. And then I'm going to run my cool bin. I have no idea right? But in theory, this could be a valid file format that should be executable, right? Okay. In this case, it tried to interpret it as like a shell script. It says, "Hey man, this didn't parse, and you had some nonsense." There is functionality that allows you to make something like this work, right? Not literally with random bytes, but an arbitrary file. What should the kernel do when it loads it? Let's see if this. There's a word I'm blanking on. I'm hoping. Where's the word? Does Twitch know? Somebody says, isn't mod probe path deprecated? I want to say on latest, like if you were on current Ubuntu LTS, it is, but it isn't on this VM. At the time the module was made, mod probe path was valid. What is the name of this goofy functionality? I'm blanking. There is a thing you can write. It's a functionality that the kernel exposes that allows you to customize how to interpret things. And there's a list that the kernel will iterate through that it will attempt to apply to parse a random file. Right? There's no shebang. It doesn't have an elf header. It doesn't have this. What are we trying to do? You can append functionality, tell the kernel, hey, try this, right? And so if we were to look at, well, I hope I have a nice link to it somewhere. Do I? Oh yeah, bam. Message. Pipe buffer is, it's its own cool thing because it has function pointers. Bin format, that's the word that I wanted. I couldn't think of the goofy thing. I was like, I know I talked about it. Okay, so the kernel can execute a bunch of different type of files. There's this functionality called bin format. And bin format allows you to inform the kernel, hey, if you see this type of binary, here is a new program you can use to try and parse it, right? And so the kernel will attempt to look at a new file and be like, hey, man, does this work as an elf? Let's try it. Does it work as a kernel module? Let's try it. Is it a shebang? All right, let's do whatever the shebang said. Is it a shell script? Right, and it just kind of goes through this process. I even linked to it. I should have just trusted my slides. And so as silly as this looks, the kernel, when I tried to execute this like arbitrary random bytes as a file, one of the things the kernel tried to do was load it as a kernel module. Okay. The list of things that it will try, I was hoping that I'd link directly to it. We'd have to jump around in the kernel source there, but it will legitimately just be like, all right, we're going to try that. We're going to try that. That worked. We're going to try this, right? And it just goes through this. And you can add something with bin format to be like, here's something else that you can try. Well, one of those things was, we're just going to try and load it as a kernel module, which sounds insane, and that's because it is. So how can we abuse bin format? Well, the way that the kernel loads kernel modules is it looks at this global variable mod probe path, which I think I can print from the debugger. No, don't print. There is just this global inside of the kernel, which is a path string to, this is the path that we execute to try and load a kernel module. What this means is that when I do the /random nonsense garbage, one of the things that the kernel does as trying to execute this is it will execute whatever path is specified in this global variable with my garbage file as an argument. Isn't that crazy? Do I get VM map? Of course not. Can PT do this? Show me something great. That sounds right. Cool. Is this writable?
Yes.
Okay. So what this means is there is a location here in memory. There's a string that if I can write to it, and then I try and execute garbage, I can get arbitrary execution. Well, I'll try and throw together a nice clean demo for next week of this literally working. Oh wait, we have the power of GDB. We can do this right now. Right? If it doesn't need to be an exploit, this should be pretty easy, right? we can set this equal to, what do I want?
Okay.
Does that work? No, why not? Am I missing like a pointer here? Evaluation of the requires the program to have a function now. I don't like you. This is supposed to have set equal. Do I need to cast it as like a char star? Oh, okay, okay. It wants to allocate. That's a silly GDB thing. Okay. Print the address of on probe. We have to be smarter than the tool we're using. I need, if I just don't tell it it's a string, I think I can still get those bytes there. Right? This is my current thought. From pom import star, and I want to context arch. Oh, come on. Context arch AMD 64. Is it just really not happy right now? Do I have pack? I want to pack the string do.py. Does that give me a number? Oh, come on. So just do it on my host system. Okay. And I pack.
You want to set the context?
No, because it turns out that's actually not actually going to matter. Do.py. Is it size equals all? Why am I blanking on this? Length? Oh, what is my argument? Find word size. Oh, I can't. When you pack a number. I just want to convert this to a number. That's all I want to do.
Like an int?
Yes. I want a hexadecimal number.
You do int from bytes.
Int from bytes b do.py.
Make sure you don't do the dot first time.
What's that?
You don't want to dot slash dot py, just slash dot py.
I know. So if we look at, it's a good question. If we look at mod probe path, it itself is a path, not dot slash. And so I want to specify do.py to be the path that will be called.
Well, the kernel resolved that to the do.py can call hacker.
No, but I'm in practice mode, so I can make root do.py. You're correct that if I were going to like fully do this as an exploit and non-practice mode, I would want it to be /home/hacker/do.py. But because I'm not doing an exploit to write these characters here, and instead I'm just trying to GDB cheese my way through, I need my path to be short enough to be an int, because what I want to trick GDB to writing this string by making it think it's writing an int. Then that's my whole game plan here. Why I'm doing this yak shaving. So I want this number, and the thought here is I should be able to do this. Right? And now GDB isn't going to complain because I didn't write a string, so GDB didn't try and call malloc from the context of the kernel. Stupid? Yes. Did it work? Let's print mod probe path again.
You know what the address is?
Dang it.
Wait.
Or did it?
What did I do? DOM new line. Oh, did I not endian this? That's exactly what I did. That's why I have the null and this is backwards. Okay.
I think you can add
How about
something like that.
Can't I do something like this? And then I need this, and then I need the zeros as well. Okay.
What did it do in the previous line?
Where's what?
Do in do.py.
You know, just gonna trust the process. I got do dot end. Why do I not get the rest of this?
You sure?
From bytes has the option to like either interpret that as a like a ending or make it like
No, but I'm reversing it, so it should all play.
but I don't know if from bytes is just gonna play well with them.
All right, you want to blame that, and so you want an argument to int from bytes, byte order.
So the same thing.
Yeah, that's the same thing. Why do I get do dot end?
So you're only able to write 4 bytes.
Oh, okay, yeah. Good. You're genius. Right? We need to cast this as a long star. Now we get it because for whatever reason, GDB was defaulting to 4 byte values. Yes. See, collectively, we all got there. And so now I have do dot pi followed by a null byte. Okay. So now let's do this outside the VM. Let's sudo vim do dot pi. Let's just print our world. I actually don't know if this is going to work or not, but at this point I'm committed. Sudo chmod plus x do dot pi. Okay, I am inside kernel, or inside the VM. I have my, where's my random garbage? Oh, my cool bin. Okay. We are here. We're going to run my cool bin, which was a bunch of random bytes. It didn't do it. I don't know if it's going to require an executable or not. Feel good about mob probe path. Okay. Let me do I'll do one last thing and then I'll like give up. But I'm really hoping that we get here. I'm going to just, for my own sanity, let's see. Why? Move, do not see. Oh, my cool bin is taking up a lot of space. Temp, then do not see. Okay. I should probably remove my cool bin. It's causing other other problems.
Is that big?
Yeah, I may have done that there. Echo slash E. Yeah, not, I don't care. It just needs to be something that's nonsense, right? Chmod plus X, my cool bin.
It's not the end.
Okay, good call. I want to do two things. I want to try this. Okay, they still did it as a shell. And the last thing I want to try and do is Kernel.h void main puts hello world CCC d.c move a.out sudo move a.out to be d.py because the names don't matter. Is that executable? It is. All right. That means that I can run this. We get hello world. I run my cool bin. I don't get why.
Can we see GDB if the path is called?
Can we see in GDB if the path is called?
Like to see if mod from path is actually like following the do.py path.
We can.
Just need to find where.
I would need. Great on call mod probe. Okay. I'm in call mod probe. That is unreadable. That's where I am. Well, I am interested in is going to be a call to like exec, because what I'm interested in is this call user mode helper setup. I wonder if I can just do this. Yeah, so I'd want this call user mode helper setup. Let's just break there. Let's break
Is it not 412?
right here.
No, 412. Or it's bigger. Oh no, okay. Yeah, that's the setup. That's the example.
Setup. Snack. Because we'll be able to see mod probe path right here.
Oh, right.
Is my thought. So if,
Should be loaded before that call.
so if I break right there before that call, maybe. GDB is not
Maybe put a start.
yeah. Okay. Continue. Okay. I'm right there. Right. Yes. So then I should be able to look at RDI.
Oh,
Okay. It is there. It is execing it. But what was one of the weird things that we saw in kernel land? I'm still not willing to surrender. Okay. I don't remember arguments to open. O create. This is what I get for being in Windows for so long. It's O create and then something. We're gonna go with that. I'm gonna write to FD. Hello.
Create and retry as well.
What?
You would need retry as well, right? You're writing to it.
Oh, yeah. Oh, is it right only?
Think you can just do read write or rewrite.
Uh, oh, RD, yeah. Read right. Yeah.
Yeah.
Um, oh, includes. Everything isn't in Windows.h anymore. Okay. Let's oh, I didn't specify perms. Okay, whatever. We will rm temp. Yeah, but we're at. Okay, so that doesn't exist. Now we'll cp a.out, sudo cp a.out to become do.py. And then if we look at do.py, it is executable, it is there, and there is nothing. There is no yeah boy. Right. Set you free. Oh, why not?
Doesn't exist.
I expected. That to get called. Okay, it is there. Okay. So what did we learn from this little exercise? Like we learned how to trick GDB, which like little pain things like this are. Oh, thank you, Twitch. It's been a while since I've been like hard stuck on something, but it's a good learning opportunity, right? So, no, because like you run into the same things, right? I don't know every trick in the book. I just kind of problem solve on the fly. Normally, you wouldn't need to be at root because for these challenges you will utilize the heap, for instance, right? Some type of kernel heap exploitation to get an arbitrary writer. At which point you have the ability to write a longer pattern. The only reason I did do.py is because I'm trying to not do the kernel exploit and just trying to talk about modprobe path. And so I use the power of GDB to just force this to occur. Now we learned a couple things by messing around with my do.py. We learned, is there a standard out from this? Wow. Right? So I can't just put the flag. But what can I do? I can write to a file. Have we seen this phenomenon before on pwn.college? Yeah. We have, right? When we try and execute a process, it's not really a process, but we try and execute a program from the context of the kernel. It is executing the binary or the file that's at the path, but the environment that program is being executed in is not necessarily the same environment that we think of when we create a process in user, right? I think we saw this in kernel security, where you had the ability to, through exploitation, execute something. Was it kernel exploitation? I think it
It was
was.
the last module 466 or the
Is
last
it-
iteration, system exploitation.
Is it in system exploitation where
Yeah,
we're in
we're
the
talking
kernel?
about it's there's race conditions in the kernel to write something. You can't since you're talking to the kernel, you can't really do a print K or
Well, you can do it pretty K, but that's
Well,
just up to DDoS.
yeah, it'd be too long. But we only had the encode to write,
Yeah.
so we could open read write to a file instead of like printing it.
Okay. There's another. There's another challenge, and I don't remember which one it is, where you can do this. You have this problem, right? Where you execute a path from the context of the kernel, and the problem is that if we were to chase this down, we would see that what this actually does, it isn't exec VE, right? Why is it not exec VE? Because we're already in the kernel. Exec VE is what you call when you're outside the kernel. Since we're inside the kernel, we're just trying to execute something. We actually don't need to build the same stuff that userland expects because we are already in the kernel, so it doesn't follow that same flow. There was something where I don't remember what challenge it was, but I show or I demo how to exec Python, and there's this weird thing with Python modules, what's available and what is. And I don't remember what challenge.
That's kernel security toward the end.
Is it kernel security? Okay, yeah. But the same problem exists where when you're executing something from the kernel, we can't just print, right? And so it makes sense to play around with this because my assumptions were true, right? Despite the fact that things weren't necessarily behaving how I thought. And so now by executing just garbage bytes here, right? My cool bin, which consisted of like EEEEFF, whatever. The kernel was like, I don't know what to do with this. It's not an ELF. Or is it? Let's try and load it as a kernel module. And when it's like, oh, I don't know, we're going to try and do that. Since I overrode modprobe path, it called my /g.py, which created yeah boy. And then the kernel's like, yeah, we did our job, right? Then this worked. Modprobe path has been around for a long time, and it has been the source of getting arbitrary execution in a law for a lot of cases where you get arbitrary right. What's an easy way to turn that into execution? Just go overwrite modprobe path. Okay, so that's kind of a cool anecdote. Questions, comments, concerns? You're going to have a good time in this module, okay? I know some of you were talking about how fun Windows has been. All right. You're going to come back to the world of Linux and be like, my gosh, this is great. This is amazing. And I love it.
Everything makes sense.
It all makes sense again. It's not going to be like, oh, I forgot how to do everything. At least I hope not. But this is a super cool module. And while the first couple levels, like this is the first challenge, I'm in the VM. If we take a look here at the challenge, there is a kernel module, right? The first 4 or 5 levels have a kernel module. Okay, you're going to communicate with it via things you already know. I don't know, mmap, ioctl. I don't remember exactly what the mechanism is, but you should see it and it should be familiar. But when you get to the later levels here, is we'll do the hard and free list right here. 6, 7, 8. 6, 7, 8 are real Linux kernel heap exploitation in a single threaded context. There's no kernel module here to let you play around. Okay, it is perform some syscalls, figure out what's going on, make it happen. All right. Now, On the plus side, very similar to heap 2, where I say, hey, here's how to heap. Stuff's inspired by this, right? Draw for inspiration. This is like that, except worse. Okay. Because the actual exploit for 6, 7, and 8 is not any of these. But if you read all of these, you will and actually understand what is happening. You will be able to say, here is a trick that was used in one of these. Can I apply that trick in this exploit chain to build my own exploit in 6, 7,
So
8?
we're not kernel robbing. Better not be. Because it says a kernel rob and it says necessary. So I thought we were just kernel robbing here.
So kernel robbing is cool, right? Have you kernel robbed? Well, you're going to in this module. How does yeah, Twitch says it's a brutal module, and it is. The jump from 5 to 6 is pretty steep. And then 6 to 7, just message the kernel. It's easy, right? Right? 7 to 8 isn't bad, depending upon what you did in 7.
2 people.
Well, no, so it depends on how you approach 7. Because the difference between 7 and 8 is that 8 has the hardened user copy, which if you already avoided this sub-problem in 7, then it doesn't matter when you get to 8, right? But if you solve 7 in a way that dealt with, exploited the fact that it was not a hardened user copy, then you have to find another path for 8. Which is why you see those two being pretty close together. I'm kind of surprised with the solves. It doesn't look like it's that brutal. I imagine they were just like very helpful people. Back when they were solving it. I hope you guys are helpful to each other. But I will say that. But yeah, so the first 5 levels involve the kernel module where you can like directly call kmalloc or kman create cache. You can just IOPTL and cause a free to occur, right? So you don't have to mess around with what is going on with this crazy syscall stuff. And the earlier ones have a dedicated cache. Like if we SB list, oh, I'm not in GDB. Is it -n? P. Okay. The cache that I'm just going to tell you, the cache that you are interacting with, because this is something that people were talking about for the first like 5 levels, is this cache right here called heap object. All right. This is a cache that is created by the kernel module. It is there specifically for that. Nothing else other than you is interacting with this cache. So this is the cache that you'll want to be looking at for the first few levels when you're inspecting. I'm bringing that up now because I don't want you to be stuck over the weekend on that. And then for the last week of class, I'm like, oh yeah, there's this heap object cache, and that's what you're working. Questions, comments, concerns? Unfortunately, it's not cool if I just do a full exploit from end to end, because then you'll just do what I do. So hopefully this makes sense. If not, ask in the Discord, we'll try and help out. If we end up hard stuck, then no one was helpful to you. That sounds like a you problem. Sorry, Twitch. If we end up hard stuck come next week, maybe we will do the inverse of what we have done historically in this class, and we'll do like an hour stream, and we'll do something real hands-on with the challenge in class for the last 2 hours. I don't mind solving, for instance, the first one or doing more hands-on demos. I just don't want to preserve that on the internet for forever. Cool. With that, I'll let you go. Twitch, do you have any last minute comments for me? Anything that I missed that seemed useful? Nothing on the Twitch end. I feel like I gave you enough time. So we'll call it there. Definitely starting this module early. It's the last thing to do. Most people don't finish it. This is the blocker for the blue belt. With that, I'll leave y'all. Somebody says office hours showing how to leak oops was a godsend. Okay, I'll keep that in mind. For you all here, you understand that like causing the kernel to misbehave or like segfault can cause an error to occur. And then you can demessage and see that output. And that output may contain a kernel address, which you could then use. Yeah. Okay. I just want to make sure because Twitch says that was super useful. That is an intended way of leaking data for some of these challenges. So keep that in mind. All right. Thank you, Twitch. With that, I'll leave you all. Goodbye. Good luck. I will see you next week.